worth it for you. So I've seen many courses around data sciences or these days learning stuff is not hard because you have a couple of places where you can go and get information. But the essential piece of learning is doing, right? So if you get a hands-on experience on some topic, that carries on with you, and then you can go on top of it. So that's the reason when I talked to Chris, we said, okay, we need to have not a talking session, but also a hands-on session. So that's why we start with machine learning stuff today. And the topic here is very specific about unsupervised learning techniques, which is more on the clustering. Okay? Why clustering? We'll talk about that. We have a lot of slides to talk about why I chose clustering. So to start with, as an introduction, who am I? I'm Raghav Jandhyala. I'm a senior director of product management at SAP Labs here in Tempe. So I'm responsible for IoT and digital supply chain products at SAP. And I also completed I'm also a data scientist from Harvard. I completed the data science certifications. And as part of my work, we do a lot of data science stuff. Also our company, has done a lot of data science since many years, especially from pricing, promotions, markdowns, in banking, retail, and supply chain. Then I'll be assisted here with Pallavi Sridhar.
Hi, I'm Pallavi Sridhar. I'd be assisting you today in the labs, so you can call me Pal, and I'd be there to assist you wherever you are stuck if you come across. I work in advanced cyber hunting in American Express. I'm not representing my company here on this event right now, but I have built a lot of stuff on my own, like voice bots, chatbots, and stuff. So I'd be a better assistant to you, and hope to be helping you through your day today. Thank you.
So it's a broad field. Again, it includes statistical methods, also artificial neural networks, and it also goes with the notion of how humans learn. How humans learn. We start with understanding the data, learning step by step. Okay, so you have some training. Similarly, machines also have some data that they learn from. So we call that a training data. So then there's a model that learns from that, and then you feed a test data. So it's something like a new object that you've never introduced to the machine, and then it can still use that model to give accurate predictions of that. So that's the level where we see machine learning. So when you come across machine learning, and you might be confused, it was also confused for me. What was the difference between statistical methods that are already out there, forecasting methods, versus machine learning? So machine learning learns from the data. You don't need to program hard rules. Okay? So there are already tons of algorithms and many things out there. It's a fast learning, fast academia. It's got out of academia and into the mainstream. And there's also a ton of research going on. Then the subfield of that is deep learning. Deep learning, you might have heard, it's very popular these days. You might have heard Google DeepMind. So where computers are able to defeat in an algo game or in the chess game, so without any prior knowledge, without any prior knowledge of the game. So there are instances where you might know Atari games, right? Older games. There are instances where a computer was just trained to look at those videos, and then it was able to outbeat humans who are playing that. So what it does, it uses something called artificial neural networks. Artificial neural networks is nothing but it is, in a way, neural networks where the learning is similar to what our human retina takes. So in human retina, when we see some object, there are neurons that gets activated, and then that goes into our memory, right? And it follows a similar principle, the artificial neural networks for deep learning. So there are different layers, there are convolution neural networks, which allow you to, when you see an image, you can extract features from them, like how tall it is, how wide it is, and then also extract the background information, like whether the light is high or low, all sort of information. So with this, what you can do is, we humans are very smart we got trained to it. If you give any image, let's say I'm a person, you can recognize me in dark, in light, whether I'm turning this way, that way. pretty easily because your brains are tuned to that. For computers, believe me, it's a very hard task. Okay, and we are with deep learning. We have come to a stage where we have up to 70-80% of human intelligence the computers could achieve. So a lot more to go. So again, why is machine learning important these days? As I said before, where it's computers' ability to learn from the data. So it's the process you prepare the data, train model, apply the model, and monitor it. So this sort of a cycle. And machines are better at making predictions, decision making. So that's why you see all these smart autonomous cars out there, right? You might also see some Uber, self-driving cars out there. Volvo is testing out. So all these are using machine learning techniques. Why now? It's because of the big data. As you know, we had a revolution of big data over the last few years. It's caught up. We have now GPUs. It's used for processing huge amounts of data and more of the graphical processing. So that's where, and then all the deep learning techniques. With that, let's look at the learning models. There are 4 to 5 different types of learnings that the machines can do. But broadly speaking, there are these 3 categories: supervised learning, unsupervised learning, and reinforcement learning. So what we mean by supervised learning, I think most of you know, is you feed the machine a group of a set of labeled data. You say that, okay, so a bunch of mails, you pass to the example to a email filter. You may say some of these are spam and some of these are not spam. So you label label the input that goes into this, and the algorithm will learn from that, so that next time an email comes, it can easily classify whether it's useful inbox or spam. There's several use cases of supervised learning techniques. We'll get to that later. Unsupervised learning. So where the machines can make sense of the data without providing any labeled information. Right? So for example, I have some data like this, where I have pyramids and cubes and so forth, spheres. So the machine is able to take this information and cluster into their real objects. Okay, so this is an unsupervised learning method. And then reinforcement learning. So reinforcement learning is more like a gameplay where you have a target goal that you want to win a game. Okay, and then as a course of thing, you'll make some mistakes, you'll make some learnings, and the computer learns from all this. The machine learns from all this with a scoring metric, and then able to understand how to be successful in the game, for example. Okay, so that's called reinforcement learning. Now, coming to machine learning techniques, many of you have mentioned that you already did regression, some linear algebra sort of things. There are many different machine learning techniques. Broadly speaking, these are different kinds. Classification, where you have a bunch of, for example, input, and you can classify 2 different labels, whether it's class A, class B, or so forth. Other examples are like clinical trial. Let's say if you're introducing a new medicine, the FDA, so they want to see whether the drug will be successful or a failure. So that's a simple binary classification as an example. Clustering. So clustering is another way where you group things. So this is also an unsupervised method. Clustering is actually also used by Google in many of these page ranking that they do. So all of the search engines that go through this, it's going through a clustering techniques. Then regression is fitting a line to your data. There are several techniques out there, including the multilinear regressions, where you have multiple variables that can affect. Anomaly detection. This is getting more and more popular, where these days it's if there's a security or cyber security or so forth, you have tons of information, and it's very hard for humans to pay attention to data and write rules like when an anomaly can occur. But machines are pretty smart at doing this. So we have anomaly detection methods, outlier detection methods that system can do. Deep learning is part of this. It has as part of the convolutional neural networks, where you have input nodes and the output, and it's more similar to your, as I said, your cognitive sense, how you process information. So there could be several hidden layers, several connections, and finally the output. Last one is the recommender systems. So when you go to Amazon or Netflix, there's always some recommendation happening, like what's the next movie you should have, what's the next product you need to buy. So there's also these recommender systems that's using machine learning algorithms. So recently I came across this article where it caught my eye. So IBM and Pfizer to accelerate immuno-oncology. So what this means is they're trying to come up with a drug for cancer. So using your body's immune system to help fight against cancer. Okay. So this is a very complex problem, and there have been tons of research papers around that. But for an average researcher, so this is very important. So for an average researcher, like somebody like you, the maximum we can read is about 200 or 300 articles in a given year. That's how much humans can only do, right? But machines can process to 25 million assets, whether it's white papers, journals, okay, or any sort of publications. You can process a billion articles a day and use all these machine learning techniques with natural language processing, using word to vec, understanding the semantics of the data, in order to come up with the summary of those articles, looking at patterns and so forth. This is a pretty big aspect here. So they are teaming up with Watson, IBM Watson. You might have known Watson was part of this Jeopardy, defeated players there. So we already see some machine learning in use, like this. And then other applications of where machine learning is. So if you have machine learning, as we saw different aspects under unsupervised machine learning, where we are interested today to go deeper. You can see broadly two areas: clustering, right? We are going to talk about that more and more. So customer segmentation, how to segment my customers so that I can sell them better products. Okay. Targeted marketing, recommender systems, what to recommend for as product recommendations. Okay. And there are several many other ones. Then there's something called dimensionality reduction. So there are cases where, let's say you take an image. An image has several properties, right? Like a height, length, width, depth of the image, and so forth. These are all we call features. So if you take a typical image, you can get up to 10,000 features out of it that you can learn, and the machines can do the correlations. So we have some techniques under unsupervised learning called dimensionality reduction, which can break down all these 10,000 features into, let's say, minimal set like 10, 15. What are the important features I can use to correlate my data? So it's a big useful for that is big data visualization, right? So even if you have marketing, right? So let's say you are a sales guy, you want to market a new product, you know your customers, like for example, the customers might have age, income, and then from social media you say get hundreds of properties. So you can do manually one after the other, right? So you feed into a machine to understand the correlation between these features. And that's where the dimensional reduction comes into play. Then reinforcement learning. It's primarily used in game AI, robotic navigations, skill acquisition, and so forth. Any of the learning tasks. And then the other broad one is about supervised machine learning, where we have classifications and regressions. Classifications are, as I said, it's used for like fraud detection, cancer diagnostics, any medical diagnostics. We can have machines now do better than even the people who do diagnostics. So it's also taking over some jobs in medical fields. Okay. Customer retention. Then in terms of regression has to do more with the time series data. So where you have history of data, you can do things like forecasting, predicting your stocks, future stock price, and so forth. So there are many aspects that you can do, pricing recommendations and so forth. So my goal in showing you all this is, I don't want to go into too much detail on the theory because you need to understand where this gets applied, so that then you can, whenever you come across in your real world some areas, you can apply the right techniques, whether it's clustering, whether it's reinforcement, with this classification you can decide. Okay. One area in supply chain and retail that we work is understanding the demand patterns. So let's say this is the sales pattern, okay, like orders for your products. So you have, let's say, one product that you're selling to the market, and it has orders from customers, right? And there's a demand pattern and there's an order pattern there. So you want to know what's the future prediction. Okay, I've been selling like this in the past. How would I go in the future? Yes, the statistical learning methods have been useful in the past to solve these. But then imagine this is just one product, okay? And typical customer like Walmart or Best Buy or others, they carry at least like 50,000 products, right? 20,000 to 50,000, each one with their own demand patterns. They have about 500,000 customers. They have the customers in the sense like it's you and me or the retailers or so forth. Then they have their vendors, right? From where they get the raw materials and so forth. So if you keep on doing this, it's a very huge problem. You easily get into trillions and trillions of data points, at which point even the traditional learning methods can't do, statistical methods can't do anything. So this is where machine learning techniques come into picture, where it looks at this, it looks at outliers as well. For example, in this period I sold a lot more, but in this period I didn't sell anything. Okay, it's able to look into all these and make fit a line curve that very well is representative of your sales pattern and can forecast your future sales. Okay, so that's one example. So then just summarizing the unsupervised machine learning techniques. Again, it's machine learning algorithm used to draw inferences from data sets. No rules based. You could define rules, that's okay, but you're not programming complex rules like promotional elimination or affinity analysis. Very complex methods out there. You're not coding any of those. Just let the machine learn from the data. A good example without any labeling. So let's say a good example here is you have given all these characters, Superman, Batman, whatnot. Machine is able to go through this and classify into the right ones. Okay, so whether it's cartoonish characters, whether it has Halloween characters, and so forth. So and then at the end, what we are doing is we have several data points, right? A data point is nothing but, let's say this is your height, this is your weight. These are data points. This represents an individual person. Okay, so that's why we call these as features. These are data points, and then at the end of unsupervised machine learning, we come up with the clusters that group similar behaviors. Okay. So again, feel free to stop me for any questions. If there are way too many questions, we'll do it at the end. But feel free to stop. I want this to be, you can keep this interactive as well. It's just for you guys to learn. Okay, so now let's talk about what is clustering all about. Okay, we have gone through a lot of examples. Clustering is a way of partitioning or grouping of items. Right? Even a small, even a toddler can do this, right? Because of the cognitive sense we have. You can arrange toys, you can arrange books, or she can arrange many different things. Okay, so humans are good at this. We want machines to be closer to this because machines can solve real-world problems other than classifying the toys. So there are big problems you can solve. So, for example, with unsupervised machine learning and clustering, we are teaching machines to behave, to understand like human recognition of patterns, to identify between living and not living, for example, animals versus plants, and sort of things, all with the data. So how does it do? So what are these examples of clustering in real world? We covered a couple of them. So you cluster products based on the sales history. What does that mean? Let's say you have Coke, right? Coke, Pepsi, all your bottled drinks. These roll up to, let's say, if you go to any of your retail shelves, there'll be an aisle completely for for beverages and drinks, and there are different varieties and different sizes and things. how do you cluster this so that I can give one pricing for a category? It's very hard to go to individual SKU level item and give a price. At the end, we want to give a pricing strategy at a category level, with beverages and so forth. And then in order to do that, we need to understand what's the buying pattern, behavioral pattern. So if I increase the sales marketing on my, let's say, Coke products, will it cannibalize or take over the sales of Pepsi products? So all these decisions are today hard-coded, but if you feed all this to machine, they'll be able to also do with the clustering techniques. Then we can talk about customers, clustering customers based on similar buying patterns. We saw one example there. Mutual funds, cluster mutual funds based on fund behavior. If you have stocks or mutual funds, every year, so you want to get an average returns, the average returns for each stock, but you want to cluster all your stocks so that you, let's say there are thousands and thousands of mutual funds out there, right? How do you know which fund to invest in? So this is where machine learning techniques come into picture, where it can cluster mutual funds and stocks based on their behaviors, how they have been selling. So instead of going with the traditional Morningstar fund classes, now the machine can tell you whether the classes are, based on how they are giving returns. It can classify those, and there are many other things.
Well, but how does it, I mean, because if you just look at past performance, you need to think, forward,
Yes.
and you need to look at, with like a fund, you have to look at what's in the fund, what companies, who are CEOs. How would clustering do any of that?
All clustering is trying to do is, let's say if you define criteria, let's say fund performance, it could be average returns over the last 6 months. Okay? So this could be varying over time, right? And then each fund might have different results. So there could be a large cap fund and a smaller fund, but the type of returns might be similar. Okay? What clustering techniques can do is, we are not going into too much detail about what companies are invested in that funds. No, those can be additional features you can get. But even with the simple ones like what's my pricing, how many units I have sold, and other information that you can see, with that information itself, you can already cluster. I have one visual at the end I can show. Okay, so then one last theory on this before we get into real clustering techniques. We talked about how can machine learning help different from the traditional learning for the unsupervised clustering methods. So let's say you have a customer base. You are a company, you have customers, this is all your customer base. I want to, at the end, cluster into the right mix, okay? It could be loyal customers, budget-conscious customers, my traditional customers, risk-averse customers, and so forth, okay? So you want a machine to come up with these things. So traditionally, we used to call customer segmentation. It was very famous until last few years. So segmentation was an older way to do this. Now we have clustering. So what is segmentation? That means you're segmenting customers. Let's say I want to sell a jacket to some customers. I would then think about, okay, is it good for males or females? Then I start with that's a rule-based, right? We start with rules. Okay, it's good for females. Then you have age. Is it good for older or younger generations? Okay, let's say we have younger generation. That's the next rule. Then we think, okay, what about the income? Are the college graduates going to use that, or the office goers going to use that, and so forth. So these are all rule-based things that traditionally you used to come up with, and then sell it into the market and see how it performs, right? And then often it used to be that we missed the real market segment, okay? That what we thought was not exactly what the market was buying. So that's why the traditional segmentation is, who is your target, right? You come with a bunch of rules, and then there are characteristics you evaluate: age, gender, income. But yeah, 3-4 characteristics you can do. But what if it goes to like 20, 30, 50 characters? Because now we have all this information these days. We know where the person lives, how long they take to commute, all sort of is information about a person you can find. And there are companies, so Google, when they take all your information, when you search all these, they're collecting all this information. Facebook, they're collecting all this information based on what you browse online. Okay, so they at the end they're making it free for us, but they're using this information for targeted marketing. So that's where clustering comes into picture. It uses this machine learning techniques to identify what should be the right targets, find relationship between points. So what's the correlation between age, gender, correlation between income versus my presence on the internet, many of these. Okay, so it finds out all these correlations between patterns, and then it can handle hundreds of these correlations and identifies the behavior pattern, which is not humanly possible.
All these examples work on historical data. If there is no historical data available, for example, a product which has no parallel in the market. Now, how do I establish relationships or data points for it? I don't have any historical data or any equivalent product in the market.
So most detailed supply chain we have concept of light modeling. So if a product I'm introducing to the market, I don't have any sales, but I have a light product, similar product that I can use the sales history of that as an input. So when you use that, or they say that I don't even care about my past, I have my future demand pattern. So I expect this demand pattern to be something like this in the future. And many companies also have demand patterns of other products. Like whenever you're selling red meat, whenever Best Buy sells, they first make predictions for the next 12 months. How much is going to be my demand for this particular customer? So this information is already there. So use that as a basis for this new product.
I have a question. So clustering is used more for, in cases like this, for exploratory analysis or discovery rather than any kind of predictive.
Yeah, exploratory, but you can use exploratory also to predict. So it also has some predict functions, and we'll see. Okay, so we talked about, so far clustering looks exciting. It's somehow seems to be over promising. Let's see what are the different types of clustering methods out there. So clustering is again a complex problem. So that's why machine learning comes into picture here. So there are different types of clustering called partitioning clustering, hierarchical clustering, density-based, grid-based, spectral, then there are 10, 15 more. So if you go to advanced clustering techniques. So the idea basically is you have a bunch of points, data points, and you're trying to assign a cluster around this. Okay. So this is called partitioning clustering, is what we will look into in more detail today. This is the k-means clustering. It's a distance-based clustering, where you find distance between data points and cluster them together. And the main thing to discuss here is partitioning techniques. At the end, there are no overlapping clusters. Okay? Every cluster has a set of data points, so there's no overlap. Then there are things like hierarchical cluster, where you see more of a tree-based clustering. We'll get into that more. Density-based cluster, so you have something like this, the data points, where there's some are too dense, some are too sparse. In order to cluster these, there are density-based clustering methods. There are grid-based one if they are more spatial, so not just two-dimensional, three-dimensional, but they're n-dimensional, they are grid-based techniques. There are spectral-based techniques. For example, you have these two sort of things, clusters, and how do I cluster these? The distance-based metrics won't work here, so we need something like a spectral base. So in this session today, we'll be covering mostly on the partitioning, hierarchical, and some density-based clustering.
I have a question. So when would you use one rather than other clusters?
So we'll go through what it does, and then we will go into details. Yeah. So just at a higher level, you always start off with k-means clustering, because it's the most easiest clustering techniques to use. Because when you start with clustering, you have some idea about how many clusters might form, whether it's 5 clusters, 6 clusters. Then you go into more of these advanced techniques from there, hierarchical, density. It all depends on the spatial aspects of your data. One thing to know is, so we are all human beings, right? Can you tell how many dimensions can we see, visualize?
3.
Three is the maximum. We can go 4 dimensions, 5 dimensions. But real world data is n-dimensional, right? I'll show you even in the lab that we are going to do, it has 4 dimensions. We are going to look at a lab where we are going to look at flower data, which has petal width, petal height, sepal width, sepal height. There itself it's like 4 dimensions. We can't even visualize that. All we can do is 2-dimensional. We can plot these two, or 3-dimensional also, and see. But then machines are able to map this to n-dimensions and find the behaviors. Let's start with k-means clustering. This is the most important clustering technique. If you mastered this, you're already one good data scientist out there. So the idea is to partition the data set into k non-overlapping clusters. What does k mean? K means just any number. So let's say if I have to classify genders, I also already know it's 2, right? So k value is 2. So it's just intuition. You know that you already have an intuition on how many clusters can be formed, and you give that as a starting criteria, and then you will classify the cluster data so that the resultant is those many clusters. So that's why the value of k should be pre-chosen. The ultimate goal of this algorithm is to minimize intra-cluster distance, maximize inter-cluster distance. So that means, let's say I have data points here. So I have income versus age. Okay. So I want to cluster my people into 3 clusters here based on income versus age. So the goal of k-means is to minimize the intra-cluster distance. So this is the cluster head. So for a cluster, we identify a cluster head, and then we want to minimize the distance here. Got it? So that every node in this cluster are tightly packed closer to the cluster head. And you want to maximize the inter-distance clusters, right? So that the clusters are far apart. Distance is just a Euclidean distance. So it's as simple as taking square root distance. So a minus b whole square. So square root of the distance. So that's all. It's called Euclidean distance. There are also different distance metrics. Now we'll start with the Euclidean distance. So our distance would be, in this case, these are all numeric values, right? So I have an income of 50,000 versus income of 500,000. So that's the calculating the distance based on this. So like any machine learning, now we are getting a little bit into the math. As a data scientist, you need to understand math also. So then the question comes around what is the problem that we are trying to solve here, right? I also already mentioned we are trying to minimize the intra-cluster distance, maximize inter-cluster distance. So the mathematical form of that is something like this, and this is what we are trying to, this is the objective function. So J is always like objective function that we want to optimize. A rule of thumb in most cases, machine learning problems are optimization problems. Okay, so they're trying to solve an optimization problem. So k-means is also an optimization problem where you want to minimize the 2 criteria I showed. So here's the distance function. So as I showed you, so let's say Cj is a cluster head, as in the previous one. So xi is any point on that. So we are trying to minimize this distance across all clusters, across all the nodes. So this is the objective function. So this objective function, they say that k-means is an NP complete problem, NP hard problem. So that means it's very hard to solve. Anybody knows NP hard? So usually, if you have like loop over loop, right? It's an order of n squared. But that's still you can complete that problem. But k-means is hard to complete. So there have been several algorithms out there. The most important one is the Lloyd's algorithm, which tries to solve k-means. Okay. So Lloyd's algorithm is a variation of gradient search. I won't go into all that details, glory details here. If you have done any Coursera course on gradient search methods, I would strongly recommend. If you are a machine learning person, gradient search, gradient descent is a must-have. Even when somebody wakes you up, you should know.
Pardon me. So this distance function, the double bars, that represents the L2 norm.
Yes. It could be L2 norm. It could be. They also have many different functions. It could be average. It could be centroid based. Primarily, it's a Euclidean distance. It could be L2 norm is one way of doing it.
All right. It's a little confusing because the L2 norm was already kind of incorporates all the summations. So why we're summing over?
At the end, L2 norm is the resultant of all this, right? Here, this distance function is just a Euclidean distance.
So this is just a distance function.
Distance function.
It's not the L2 norm.
No, it's not L2. The whole
It's
function
one
would be.
step ahead of L2 norm. So this
Okay,
one
I'm
would
just
lead
confused
you
with the
there.
notation. That's all. I mean, because statistically,
There are several
L2 norm
notations.
already incorporates the summation.
This is what you'll find it hard, right? When machine learning, there's no standard yet a way to represent things. And I wish there's like a statistical institute or those who can standardize on these equations, because this is still an academia thing. Okay, so how does this algorithm work? The algorithm is pretty simple. You select k points at random as cluster centers. Don't worry if you don't understand this, we have examples that follow. So we start with random k points as the cluster centers. Okay. Then you do assign objects to the closest clusters. So each point you assign to the closest cluster. And then you recalculate the mean. So you started with this as the cluster center. Now you assign each point to a cluster. Then you reassign this to find the mean of all the data points and move it around. Then you repeat the whole all these again, where you see which points move to which cluster, until the clusters don't change, until they're stable clusters. Okay, so we'll go to example. If you're in Python, this is just one-liner. So you use k-means equal to this function called k-means plus k-means. There's an algorithm called k-means plus plus, and then you define number of clusters. Random state is just to give the same results every time, and you fit to your data. So just one-liner in Python. Okay. So now let's understand the inner workings of this algorithm.
Could you impute a k point, or you have to pick?
You have to pick a point.
You can't say, let's make this a fake.
We'll look into that. The how to initialize your clusters. So let's start with some random points. This would be your income, age. So everybody understand features? Features now you understand. Features is like any numerical value here, like age, income, and this is your population. Let's say these are all your people in the group. Now k-means algorithm first starts out with cluster heads. So in this case, I start with k equal to 2. So I randomly assign any 2 points on this. Okay, it's a random. Then once you assign the random point, then you can actually draw a hyperplane between these two. So let's say I draw a line between these two and I draw a vertical line. So in a sense, all points that are left of this will belong to this, right of this will belong to this. But in other words, for each point, you're finding where it can fit. You're finding the distance, right? So in this case, this point belongs to this cluster, this points belong to this cluster, and so on and so forth. So we are in a way looking at all points again and reassigning them. Good? So we have now got these red points. So this is one cluster, this is another cluster. Are we done yet? No. What we need to do is now we find the mean of, so we shift the cluster to its mean. So when we shift the cluster, we find the mean of all the points. So we are moving from here to here. So this is an artificial point. So this cluster is not even there in the data point. So this is an artificial point. Good. Now we do the similar exercise. You find the new cluster heads. You define the hyperplane around that. So all points that are left of this will belong to this cluster and right. So previously this point which was yellow will now become red, right? It belongs because it's closer to this cluster now.
In those cases with the means.
Yes. So now this one is a mean of yeah. So it shifted. If you remember, it shifted from here to here. You're taking mean of all the points. Okay. So that's good. So okay, now we do similar exercise. For all these points, the mean now shifted from here to here. Okay. Mean is just like arithmetic mean. So you take all the points, divide by the number, right? Okay. So again, you do the hyperplane. All points on the left belong to red cluster, right belong to yellow cluster. That's it. So you do this until there's no cluster changes, and you arrive at your k-means cluster. Okay? So this is a very simple way, elegant way to cluster data points. Okay? So at the end, what have we done? So we increase the inter-cluster distance, reduce the intra-cluster distance. Okay. So coming back, what is k-means clustering? So we have k-means is solved using Lloyd's algorithm. Okay. So as I mentioned, Lloyd's is one way to solve the k-means problem. So there are also some drawbacks of k-means. It does not work well if the initial points are too close. Since we have random points, right? So we choose random points. So if these points are too close, the k-means doesn't converge faster. So, but then there are methods like optisim, which are used to assign the initial points for k-means. So this is where you can use still to assign initial points. The k is still 2. Where you want to see the diverse set of points. You want to have the points at very much distant, so that you can start the k-means clustering. Okay. So this is also less sensitive to outliers and missing data. No, actually it's highly sensitive. Sorry. So this is highly sensitive to outliers and missing data. So if k-means, if you don't provide one point, or if the point is too high, if it's an outlier, since it's a distance-based metric, it will take that point into account. Let's say in our previous, if all these points are okay, but there's one point all the way down here, it's an outlier. So it can really spoil the k-means algorithm. So that's why outlier detection is an important thing in the k-means. So we have methods to do that. But also if you have missing data. So here, that's why if you have missing data, you have to, let's say you have to, first of all, you have to normalize your data. Yeah, so that you don't have huge variation, and if there are any missing points, you can use any of the missing points algorithms out there to fill that before you do k-means.
So to your point, sir, on the practicality of why, I mean, if you feel a little lost here on the technical aspects, how many of you have had cough syrup in your lifetime? I'm sure practically everybody had, right? Have you ever seen the dosage where it says, if you are an infant, doctor recommended, if you are aged between 1 and 5, you take so-and-so dosage and it has to be a children's syrup. And if it's an adult and if you're over 6 and whatever, you take 20 ml per 6 hours, right? So how did anybody ever arrive at such a data? So they have clustered a group of age group and a particular dosage recommended for that age group. So if you go back on your slide, Raghav, so you're seeing a red, green, and yellow. So it could practically be an infant versus a kiddie syrup versus adult syrup, right? I mean, adult syrup and their dosages, how they have determined it, right? So you practically have clustered them, and you are trying why the age of 6 and above, right? You just asked, what is the breaking point, right? You are clearly saying 6 and above go to the next level of syrup. So how the K at random point, how you are trying to baseline that group between 0 and 12 months versus 1 and 6 year olds versus 6 year olds and up is kind of using this methodology to come up. At the end of the day, practicality in past, statisticians used to use the data that they had and how much dosage was good for what age, right? They used to do this practically sitting on paper, but right now the machines can predict it for you. It's not just in a drug world. Even if you look at, let us say tomorrow, Amazon or any online firm that wants to set up their own shop, they are gonna go do this, let the machine do their job for them and tell them where should the next warehouse be set up. That'll make it easy for them to transport the products easier, because majority of the requests are coming from that particular geolocation.
So let's look at one more technique, hierarchical clustering. So if you remember in k-means, the main thing was to picking up a k, right? So it was more important. So unlike that, hierarchical clustering there's no need to choose your initial k value. So the way this works is there are two aspects of hierarchical clustering. Agglomerative clustering, which is bottom-up clustering, and divisive, which is top-down. So let's say you have data points here, A, B, C, D, E, F, G. Agglomerative clusters starts off with every point as its own cluster, and you build your clusters based on some distance until you come up with one cluster. Okay? And then divisive is the opposite. You start with one big cluster, and then you divide that until you reach individual clusters. At the end, what is the value of, how do you then know what clusters? There's something called dendrogram, which you'll see in the next slide, where you cut this tree, and then that will give you how many clusters that are formed. So dendrogram is pretty much used for hierarchical clustering, where it gives you like a tree type clustering aspect. So it's a tree representation of your data points into clusters. So let's say this is an agglomerative cluster, where it says bottom-up clustering. So let's say these are all your data points down here. So the root node, so the top one contains all your data points, whereas your leaf contains individual data points. Right? So then you can cut this dendrogram at a different level, and at what level to cut you can also derive from some. We have some cluster evaluation metrics I'll show later. So then you can cut this cluster, and then you can say, okay, when I cut this, 1, 2, 3, 4, 5, 6, let's say there are 6 clusters that are formed. If I cut it here, maybe there are just 3 clusters formed. So if I cut it here, there are 5 clusters formed. Okay. So where this gets used is many of the planners have some sort of idea about how many clusters can be formed. And then they use this as a starting point and say, okay, if I cut my data at 5 clusters, how does it look like? If I cut at 3 clusters, how does it look like? So they can use this. Now let's look at an example of how hierarchical clustering works. Okay. So let's start with our data points. We have 1, 2, 3, and 4 data points. Okay. Now we start off with the pairwise distance matrix. What is the pairwise distance matrix here? Means between every point we are finding the distance. Here it's a Euclidean distance. Okay. So let's say you have come up with data point 1, 2, 3, 4, and the distances between each of these. And the diagonal is 0. Why?
Share distance from yourself.
Yeah, the 0 distance from yourself. And why is the bottom left triangle not diagonal not important? Duplicate. Symmetric. Right? The distance between 1 to 2 is same as distance between 2 to 1, so we can ignore the bottom part. So the first step in the algorithm is to find the minimum distance. Okay, so of all these data points, 0.3 is the minimum distance. Okay, so what that means is now we want to merge 1 and 2 because that's the lowest one. We want to merge 1 and 2 and make that so 1 and 2 will be merged into its own cluster. Okay. So well and good. So we if you merge 1 and 2, there are different methods to merge, okay? And we call this linkage, okay? So linkage is the distance-based metric on how for example, the trees should be merged. We'll come to that in the next slide, okay? Just for now, forget about that. So then we merged 1 and 2, okay? And then we chose a linkage method called complete linkage. Okay? What complete linkage does is, when I'm merging 1 and 2, I'm merging 1 and 2, right? If you look at this, we want to take, for node number 3, we want to take the node, the distance, the max distance, so this is 0.5. So that's what we want to take. So complete linkage uses the max function of all the nodes available. Similarly, for number 4, between 0.7 and 0.8, 0.8 is largest one, so that's the one we're going to use. This is how we are going to use for merging. So okay, we have merged these two. Now we got the least one here. Least one is 0.45, right? Of all the data points. So that means we are going to merge 3 and 4. That's what we see here. We are merging 3 and 4. So at the end we have merged 3 and 4. We have merged 1 and 2. The overall distance height is 0.8. So a dendrogram represents the height of the cluster, which is the inter-cluster distances. And this is how hierarchical clustering works. Any question on this? Okay, understood. Okay, so I was talking before about this complete linkage, right? So I was talking about max complete linkage. What does it even mean? So linkage means how to find new distance between nodes and subtree. So we know that we have node 3 and then we have merged 1 and 2. So how do I find the distance between 3 and the new, because this is no longer one node, right? It is a tree. So a node to a tree. So how do you do that? So for that, there are different cluster distance measure: single link, complete link, average link, centroids, wards. So these are the top 5 methods with different calculations on how that works. So we chose one method, which is the complete link method, and this is by default chosen one of the most used hierarchical clustering method. So in complete linkage, we are doing the max of all nodes. So that's why from 3 to 1 it's 0.4, 3 to 2 is 0.5. Okay. So the new distance between 3 and this merged one is 0.5. Similarly, if you have one with a single link, you have one with the minimum, which is 0.5. And this is what, as a data scientist, you need to evaluate for a clustering. For the distance, you first start with a single, complete, average, then you see how the clusters are forming, and then evaluate these clusters. So let's look at the benefits of hierarchical clustering. It's easy to understand, right? For many of the data scientists, it's very graphical represented, so it's easy to understand. You just need to pick one linkage criteria, whether it's single, complete, average, or so forth. That's it. But this is performance intensive. Why? Because we are doing this pairwise matrix. Every time we are finding distance between every node. So this is more performance intensive. But there are other methods like reciprocal nearest neighbor method that can be used to reduce this computational complexity. How do we, in Python, how do you do this? So the Python has very nice, Scikit learn has this agglomerative clustering method. All you need to give is, you don't even need to give a number of clusters. I think you just give a linkage, you give the fit of data. If you want, you can also give the number of clusters. Okay, so far we learned 2 clustering techniques, k-means, hierarchical. Let's look at the leader cluster. So one of us, you asked like, how do we know how many clusters should I choose? In k-means, it's k is given by you, right? But what's the best way to start with the initial value of k? So that's where this leader cluster can be useful. So this is used to, in general, to cluster large data sets. So how does it work? For every point, you find what is the closest cluster, if there's a cluster. We'll see an example, okay? For every point, you see what's the closest cluster. And if it's in the threshold of that cluster, it belongs to that cluster, or it will form a new cluster. So let's look at the example. example always helps. So as you see, let's say we started off with a point here. You can randomly choose any point, and you draw a radius around it. Radius can be any radius, any distance that you think about. So let's say I'm age. Let's say I want to choose an age group. I want to start with the age circle 5 years above this node. Okay. So just any metric. So you start with the radius. Then you do that for all points. So next I pick any point. So for example, I pick this point. So does this belong to that? Is it in the radius of that? No. So it creates its own cluster. Now you pick another point. So this point. Does this point belong to the radius of any of those? No. We draw our own cluster. Now we pick this next point here. Okay. Does it belong to the radius of any cluster? Yes. It belongs to a cluster of this. So now this can be part of this cluster. So on and so forth. So until all the points are done. So you end up with some number of clusters. As you can see, this is blazing fast. It's linear. So there's no distance computation or anything. All we are doing is picking all the points, which one is the closest, if not forming its own cluster. So this is more of a space filling algorithm. Eventually, every point in the cluster gets assigned to a cluster or forms its own cluster. Again, it's distance based. It's really fast. At the end, what you get out of this is the value of k. So after you do all this, you find out that I come up with a k value of 5 or 6. Now you go back to k means and then do the real clustering. Understood?
Does it update the centroid of the cluster?
No, this doesn't update any centroid.
It's just classified.
It's just classifying.
It's
Yeah.
called a leader cluster.
It's called a leader cluster. There are methods where it also updates the centroid, but those are advanced ones. So, so far we have looked mostly on the distance-based, but there's also density-based clustering. What is density-based clustering? So one example is dbScan is one clustering technique. It's a very long density-based spatial clustering and application of noise. So what does this mean is, we as humans are very good at identifying clusters, right? So if I give you this shape, you can easily tell me 1, 2, 3, 4, 5. There are 5 clusters here. But for computers or machines, they need to understand the spatial or the density aspects in order to say which one is clustered, how to cluster. And then there are outliers. If I look at this, I can form a cluster here, cluster here, cluster here, but I cannot form clusters for any of these, right? So these are your outliers. So this is where density-based technique is very useful. It's used for outlier detection. So we talked also in the beginning anomaly detection, how to make sure we have large identified anomalies. dbScan is very good at identifying these anomalies. So it can also be used as a starting point for k-means, because in k-means it's very sensitive to the outliers. So this can be used to initialize this. Okay, how it works? This is also pretty straightforward. So we label each point. So let's say these are all the points. There are only 2 things that you need to choose. One is how many neighbors. So let's say I want to start with 3 neighbors here, and then the distance. So distance means the radius. Okay. So these are the only 2 criteria we start with. So we identify. So I start with the minimum points equal to 3. That means I'll form a cluster only if there are at least 3 points in it. So we randomly again choose any point. I draw a circle around it. So that means these 3 other points can belong to that cluster. So we call these. So we call this one core point because it can create a circle in which 3 other points can fall. Right? There's this one called border point. So a border point belongs to a cluster, but it is not something which can form a cluster. Then the last one is noise point. So it is outside these clusters. No matter what, I cannot bring them into any cluster. So these are your outliers. Okay. So this is again, it's a simpler method. The main criteria is to define. So we always in machine learning we think of a call things like hyperparameters, right? What are the parameters that you can tune to get a model correct? So the min points and the distance is usual. Distance, min points you can use like k nearest neighbors to come up with this distance metric. Again, what are the advantages? You don't need to specify the number of clusters. This is another way to find the number of clusters. Okay. So it's also sensitive to the value of radius or epsilon. So if the epsilon is too small, then you have sparse clusters. So what if I have the distance is too small? You have very sparse clusters, right? Small clusters. If this distance is too huge, I have very big dense cluster. So it's always important to choose the right value of epsilon. So how does it work? In Python, it's again a straight one-liner, dp scan. Epsilon is the radius. Min samples is how many nodes of that cluster, and you fit your data.
And the right value, I guess, depends on every data set. Right?
Every data set, yeah, exactly. It depends on every data set.
Right value, I meant with radius.
Yeah.
Choosing that radius.
Yes. If you look at the documentation, they always start with 0.1 at least, and then there's the elbow curve. We'll talk about that in a bit, which can be used to identify. Okay. I think we're too much TV. I think we are getting closer to finishing. The last one here is spectral clustering. So again, spectral clustering is again works for any shaped clusters. So if you have a cluster which looks like this and another concentric circles, or you have irregular shaped clusters, irregular shape, you can use the spectral clustering. This is more advanced. It has eigenvectors, eigenvalues, that sort of a map. That's why I didn't want to put any slides, it will throw you off. So important to know that it uses eigenvectors and eigenvalues in order to come up with the cluster. The simple concept here is we've come up with a matrix, a graph matrix of every point and its distance. Okay, and then using the eigenvectors, eigenvalues, we can cut at what point it can form a cluster. So you can form a cluster here, and you can form a cluster here. This is useful in social media. So let's say I have a bunch of friends, my friends have a bunch of friends, and so on and so forth. We are very much a connected network. Okay, so if I have to reach, or also in LinkedIn, if I have to reach from one person to another person, I have 20 different paths to reach. Right? But what's the best path, or that one person can connect with the other person, or to even understand? This was where one person asked whether we can use prediction for it. This is where prediction also comes into picture, saying that I can form, right now there's no path between 1 and 4, but once I form a cluster, maybe in order to connect these two clusters, a node between 1 and 4, if I can form such a node, that will make these clusters more connected. So that's where you see your friends' recommendations in Facebook or LinkedIn recommendations. These are using some of these techniques. Okay. All right. Very good. So far, all these clustering techniques we looked at. K-means, hierarchical clustering, leader cluster, DB scan, spectral cluster. These are more than enough for you to get into the space of unsupervised learning. So then how to visualize the clusters, right? So if you're a typical data scientist, visualization is the number one thing that you have to pay attention. There are techniques like parallel coordinates. This is available in Python, where let's say this is a feature, second feature, third feature, fourth feature. We talked that we cannot visualize more than three dimensions, right? So this is parallel coordinates where now you can see multiple dimensions, okay? And then you draw these, relationships. Just plot the data. And here you can see these are sort of my clusters formed between all these. So these are different breeds of the flower breeds, and based on different values of the petal length, sepal length, and so forth, different clusters are formed. Other one to use is tree map. So it's a very good visualization technique to see how it can group your data. We also talked about dendrogram, right? This is another visualization. Now, last few slides, let's talk about the cluster evaluation. So, okay, now that you have done your clustering, it's not over. Very important thing is cluster evaluation, whether your cluster is good enough. Okay, any machine learning techniques have to go through evaluation. You just can't throw in numbers back to your people. It has to be proved. So the simple things is, first of all, in k-means or anything, is to how to identify the number of clusters, right? Very simple starting point is, if you have n nodes data set, square root of n by 2 is a simple metric. Okay, so let's say if you have 100 data points, okay, 100 by 2 is 50, right? So roughly, if you do a square root, like 7 clusters is typical clusters that are useful. This is without evaluating any clustering techniques. Then we have something called elbow plot. So elbow plot is, what we are doing is, we can run k-means for every value of k. We can run k-means for 1k, k is equal to 2, 3, 4, 5, 6, until whatever. And then this is your intra-cluster distance. So k-means will give you a value called intra-cluster distance, and we measure the intra-cluster distance. So as you see, we want to find the clusters with minimal, with where there's less number of clusters and less of variation within clusters. Okay. So in this case, if you take like a hand of elbow, right, you want to find the point at which it curves. Yes, this is one candidate, but the best candidate is here. So this is called an elbow curve. So that tells me that I want to take number of clusters equal to 3, and this could be an evaluation. This could be your starting point for your clusters. So important to know the elbow plot. Then there are some cluster quality measures. Let's say you know your ground truth. So this is intrinsic method. So what does ground truth mean? That means you have some idea about your labels. That means, for example, genders, like you know whether it's male or female. So if you have some sort of an idea, and then you cluster your data, you're then comparing your results of your clustering versus your truth. Okay? So there are measures like cluster homogeneity, cluster completeness, V measure, and so on and so forth. This is all available in your Scikit learn. We'll see in our labs as well. So here there are measures checking that is every member, if the clusters are non-overlapping, that's important. We don't want clusters to overlap. And then we want to measure the completeness of clusters. So these are some measures. So the higher the value, the better cluster quality. Last cluster quality measure is silhouette coefficient. Again, important measure. So all it's doing is, we have talked about inter-cluster, intra-cluster distance, right? It's just doing that value. So B minus A by max AB. So B is the nearest cluster distance, A is intra-cluster distance. Okay? So it uses some math and finds out this value. And there are some methods to plot these. So you can see I can plot these into 4. For my data, I plotted into 4 clusters. Then you can visualize this thing. And this is the silhouette coefficient. So it shows that if you look at the values on the right side of this line, okay, first of all, this line is closer to 1, so which means it has a very good cluster. And we want to make sure that the clusters are uniformly distributed, uniform in shapes. You don't want one cluster which is very, very thin like an icicle and one which is fat. That's not a good cluster. Okay. So this is where this silhouette analysis is useful. A value closer to 1 means it's a good form cluster. If the value goes negative, that means it didn't do a good job in clustering. Okay, that's it. So then this is a whole list of what's available in Scikit learn in Python. So you see there are a bunch of methods: k-means, affinity, mean shift. There are more than what I mentioned. They are Gaussian based, so using probabilities for clustering. And it has a very good idea of where they are used and whether it's distance based, Euclidean, and so forth. So So this is already there. If you just search in Google for Scikit Learn clustering, you'll immediately land into this. Yes?
Do we have access to these slides in the presentation?
Yes, I'll try to. Do you guys need it? Because I have to put references if I took any something like this. I have to put some reference down there. Then I'll send out.
Just, I thought this is the most useful ones with the last view where you were talking about how to understand the quality of your customers.
Yes.
You just go with it. You can just go
Oh yes.
And I'm recording this.
You will actually walk through them in the labs.
Yeah.
So I think labs with the hands-on will be more useful to you.
Last, there's also Scikit Learn also has this very nice picture of, let's say if you have a different shape, different shapes like this, how each of the clusters clusters them, and which one is best over other one. So again, I think there was one question asked, which one is the best clustering method? It all depends on the data and first of all, it depends on the data, the features that you have. You always start with k-means. You'll never go wrong with that, and then expand on top of it.
Is there like a metric where you could like compare the different like algorithms and see how well they cluster?
Yes, and that's what it is.
Obviously,
So in a way, these are all the algorithms, and these are visualization, but then they are
is there like numerical?
numerical values. So the one that we saw before, the numerical ones, silhouette scores and those, you can compare for each of these and determine what's the best one. Okay, so that's all for the clustering. So let's again think about where this is used. A practical application is handwritten digits. So computers can understand handwritten digits, like whatever you write, and cluster them. In this case, 10 different clusters. Okay. So this is, in a way, these are 10 different clusters, each of these, each one with its cluster head. And then it can point each of these data points. These are all these data points, and it clustered them without any knowledge on rules or anything. We don't put any rules like if it's tilting this way, or put it in this cluster. There are no rules. The machine understood from this, came up with this. And this, you see, the cluster quality measures. So based on different clustering techniques, you can see what is the homogeneity, completeness, and different methods. So you see its homogeneity completeness is closer to 0.7, which is good enough. If you get to 0.8, 0.9, it's very good.
In this one, the silhouette is not very close to 1, right?
In this one, silhouette is not close to a good observation. Yeah, this is coming from, again, Scikit Learn, because I think all they have done is taken the data, plotted it out with k-means and so forth. But then hereafter, you have to do all these feature engineering, then coming up with what's the best quality cluster. That's the job of a data scientist. Okay, here we also we heard about PCA, Principal Component Analysis. Did anybody hear PCA? Very important. It's used to reduce your features. If you look at this handwritten ones, these are images, right? Once you plot, there are like about 5,000 features. Because the image is like big pixels, right? So it's like a feature. So using PCA, they were able to get to 64 features. Okay, that's it. So these are the ones in future. I plan, we'll discuss with Chris. There are several topics which we can bring to the community of advanced machine learning stuff. One is principal component analysis, how to reduce your dimensions. Supervised machine learning, some classification techniques. Deep learning using convolutional neural networks. So how do you take an image like a cat, or how does, for example, Tesla take an image of this and do object recognition. Network analysis like Facebook, social media analysis. So if you have a network, you are connected to someone, someone is connected to someone, you can say who is the most influential person in the network. And we can also predict who is going to be your next friend. So then regression and time series analysis. So if you have time series, you can do all sort of regressions, ARIMA, SRE, SARIMA, SARIMAX, a bunch of them, to identify seasonality, trend, outliers, and so forth. Natural language processing, word-to-vec, bag of words. I came across one project where we did Shakespeare sentiment and Shakespeare analysis, where we gave a lot of Shakespeare text books and said which chapters were written by Shakespeare and which were not. So that sort of thing computers can do, and then also computers can tell the summary of a book. So, okay. Twitter sentiment analysis. So you have Twitter feeds. Let's say you go to McDonald's, you don't like the coffee, you put something on Twitter. Okay. Trump tweets all the time, so we can see what's the sentiment in general for Republicans versus Democrats. So that sort of analysis can be done. So this is the power of Python where it can come. We have libraries to do all this. So we'll think about some future sessions around these to be more hands-on, to get to so that you're ready for this. Okay, so that's it. We'll take some break, and once we come back, I'll walk you through quickly on the lab. What are we going to do? That's it. Yeah. Okay, so we'll take a 10.
And guys, I hope all of you received your prerequisite for the lab from Chris this morning. Did you happen to or did not? If anybody have issues downloading Python, let me know.
Python and Jupyter are prerequisite. Has everybody installed, or anybody needs assistance?
I'm here. If anybody needs assistance, I'm right here.
Okay, so you're all good with starting, right?
Okay.